Chapter 12 begins the study of complex numbers for us, and they are used especially in the field of electronics. What's extremely unusual about complex numbers is that they are going to help us to deal with the square roots of negative numbers. The square root of a -4, for example. Prior to now, we would have no way to deal with that because the square root of a number is the value that when you multiply that value by itself, you get the number under the radical. Well, there is no number that you can multiply times itself. You know, a -2 times a -2 is a +4, not a -4. And again, it's got to be the same number. So we're going to be dealing with square roots in this chapter. We're going to look at these complex numbers in three forms. One is called rectangular form, and in rectangular form, a complex number is going to be a binomial, just like 2x plus 7 is a binomial. And we're going to add, subtract, multiply, and divide those binomials. And so it's going to be very easy to do because if you take this 2x plus 7 and add 3x, I did say add 3x minus 4, you just collect your like terms. So 2x and 3x is 5x, and 7 and a minus 4 is 3. So that's kind of the concept. I'm going to go ahead and erase this. Before we do that, though, I'd like to simplify a radical. So the one I'm looking at first here is the square root of 50. So to simplify a radical, you need to think of the number 50 as two factors. You know, what two numbers multiply to be 50? You know, 5 and 10 multiply to be 50, but they're not the numbers that I'm looking for. I'm looking for two numbers where one of them is a perfect square. A perfect square is a number that you can take the square root of and get an integer. So 4 is a perfect square because the square root of that is 2. 9 is a perfect square because the square root of that is 3. 16 is a perfect square because the square root of that is 4. 25. And of course you get these numbers by taking the integer and squaring it, that if you took the square root of 36, you would get 6. So that's how you get that list. So you want to take the biggest number from this list of perfect squares and factor the number 50 into that. And then once you're there, in order to simplify a radical, the square root of 25 is just the number 5. And you bring down the square root of 2, and I'm done. I've simplified the radical. You can compare this to taking the fraction 2/4 and writing it as 1/2. I have simplified the fraction. This is the form that mathematicians wish to see this in. It's simplified form. So in my list of perfect squares, I wonder what number, oops, didn't mean to erase the 36. I wonder what number is the biggest number that is a factor of 200. And while 25 is a factor of 200, 100 is the better number. So I'm going to think of 200 as 100 times 2. That allows me to take the square root of 100 and call it 10 times the square root of 2. Done. This number right here cannot be factored again, where one of these numbers would be a factor. All right, I'm going to do the next one incorrectly. So let's say you see the number 80 and you're looking for a number from this list that goes into it, and all you can see is the number 4. So you go with 4 times 20. That is 80. And so you say to yourself, well, square root of 4 is equal to 2. But see the square root of 20? It's not done. It could be broken up into 4 times 5. And the square root of 4 is 2, so you have 2 times 2 here, which is 4, times the square root of 5, and now you're done. So if you don't find the biggest perfect square first, in this particular case, it would have been better to use 16, because 16 goes into 80. Take your calculator. 80 divided by 16 is 5, and then you would have gotten the answer much more quickly. 4 times the square root of 5. If there's a letter involved, so the square root of 25x squared, we're not going to deal with we're just going to have values for x be positive, so we don't have to use absolute value brackets. I'm going to leave that topic off here at this time. This is how I'm going to think of this. So the square root of 25 is 5, and the square root of x squared is x, because x times x is that x squared. All done. All right, cube root. What do I need to do there? Well, the cubed root of 8 is the number 2, because 2 times 2 times 2 is equal to 8. So now when I'm looking for cube roots, I'm looking for a number that you would multiply times itself 3 times to get that value under the radical. So I'm all done with that one. So the list of perfect cubes is generated by starting with the number 2 and cubing it, giving you the first perfect cube, which is 8. The next one is generated by 3 cubed, and the number 3 cubed, 3 times 3 times 3 is 27. The number 4 cubed, 4 times 4 times 4 is 64. So in this number 54, I'm looking for a number from this list that divides into it, and I believe 27 does twice. I believe that 27, and I'm going to actually write this separately, times 2 is 54, and then here I'll have that x cubed. Of course, these are all cube roots. Sometimes I forget to write that. And the cube root of 27 is the number 3, and the cube root of x cubed is the letter x, because x times x times x is x cubed. And then what I have left under the radical is the number 2. And I'm all set. I'm all done. Okay, I'm just going to real quickly develop the imaginary unit. So in order to deal with square roots of negative numbers, mathematicians some time ago decided to establish, typically it's the letter I in mathematics, but in our course, because we're in electronics and drafting and design and mechanics, we use the letter J because I is used for current. So I'm going to establish that the letter J is equal to the square root of a negative 1. And by that definition, so this is just a definition, you know, the square root of 4 squared, because that's what I'm going to do next, is equal to the square root of 4 times the square root of 4, which is equal to the square root of 16, which is equal to the 4. So when you square a square root, you just get the value under the radical. So by this definition now, what I'm going to do is square both sides of this statement, and I'm going to have that j squared, therefore, is equal to that value under the radical. So again, here's the definition, and then from that we develop the value for j squared. We need to memorize these or be able to create this for ourselves. Let's go on. So now what I'd like to do is I'd like to simplify something with a negative number under the radical. So what I'm going to do is I'm going to write the square root of a negative 25 as the square root of a negative 1 is 2 factors times the square root of 25. We just defined this as the letter J. But the square root of 25 is 5, and because in mathematics when I have a coefficient in front, I usually put that in front of the letter. So the square root of a negative 25 is equal to 5j. You know, I could keep doing this over and over and over again. I could go with the square root of a negative 100, which would equal the square root of a negative 1 times the square root of 100. But I'm going to tell you from now on you don't have to write this step out, because this is equal to j, and this is equal to 10. So the square root of a negative 100 is 10j. So right here, the square root of 49 is just 7j. And then out here, I want the opposite of that, so I'm going to bring that sign down. So my answer for that one is a negative 7j. If you took your calculator and took the square root of 0.36, you'd get 0.6. But because there's a negative sign under the radical, it's 0.6j. And because there's a minus sign in front, I'll bring that down, and I'm done. If I have here the square root of a negative 63, that one's not a perfect square. So I'm going to think of it as 9 times 7. But I'm going to make the 9 the perfect square number. I'm going to make that one have the negative sign so that I can call this 3j, bring it out from under the radical, and then square root of 7 to follow. Just going to go ahead and finish this page, I believe. I do want you to know that a complex number now is going to be in terms of two terms. A is going to be called the real part of a complex number, and b times j is going to be called the imaginary part of the complex number. So we call the square root of a negative number an imaginary number. So for example, on this problem right here, we've defined already just on the previous page that the square root of a negative 1 is just j. I'm going to bring down my plus sign, and I have written this in rectangular form. I've got a real number and then a term with j in it. Let's do it one more time. So square root of a negative 64 is 8j. All you've done is taken care of this. That's what's 8j. You bring down your minus sign. You bring down your 17. This is the real part, and this is the imaginary part of that complex number. The square root of a negative 72, I'm going to write it over here. I'm going to think of the square root of a negative 72 as, the first thing that came to my head was 9 times 8, but 8 has a 4 in it. So actually it's probably supposed to be 36 times 2 is 72. That would be faster. The square root of negative 36 is 6j times that square root of 2. I'm going to put that right here in place of that square root of a negative 72. And I have simplified this expression in terms of j.